Hello students, welcome back to the classroom point. In our today's class, we are going to discuss the particle nature of the electromagnetic radiation. In our previous class, we had finished a class on the wave characteristics and the different type of the electromagnetic radiations and the relation between the different characteristics of the wave. So let us see now and what is the things leads to the discovery of the particle nature of the electromagnetic radiation. So here wave nature of the electromagnetic radiation or the light was unable to explain certain things. They are, the first one is wave nature could not explain the black body radiation. Second one is photoelectric effect. And third one is variation of heat capacity of solids as a function of temperature. And fourth one is line spectrum, particularly of the hydrogen. So wave nature of the light or electromagnetic radiation was unable to deal all these things. It was successful in explaining the diffraction, refraction and all those things, but not able to explain these things like they are black body radiation, photoelectric effect and variation of the heat capacity of the various solids as a function of the temperature as well as the line spectrum. So to deal with all these, let us discuss how we can see the objects and what are the properties of the objects when light falls on a particular object. So let us take a particular object at a particular temperature T. How we can see this object is, so whenever light falls on the object, we know that light is a form of energy. So when light falls on the object, a part of the energy got absorbed by the object and some of the energy get reflected. And whatever the energy get reflected, this is reflected. So this gives color to the object. That means we can see the color of the object. So whichever color get reflected, so the object appears in the same color. We know that white light is the combination of 7 colors. They are Vidyar, violet, indigo, blue, green, yellow, orange and red. So when these 7 colors are mixed, that gives the white light. So when white light falls on a particular object, as we said here, a part of the electromagnetic radiation got absorbed. Imagine out of these 7 colors, if red color is not absorbed, if it reflected, so that the object looks in the red color. What happens if green color not get absorbed but reflected, then the object looks in the green color. Sometimes apart from these 7 colors, there is a different colors in which we can see the object. For example, a part of the red light is not get absorbed and that mixed with the white color which produce the pink color. So pink is the combination of the red and white color. So more the white, lighter the pink color, and less the white radiation and more the red color that mixed in the white color that produce the darker pink color. So finally here, if apart from these 7 colors, if you see any other color, that color is the combination of the more than one color. So that for example, if green and red is not absorbed and they get reflected, so the combination of both green and red produce the new color. Usually it is the yellow color. So that here whichever color is not get absorbed and those get reflected, that gives the color to the object. So finally, if more than one color, if mixed and produced and get reflected, the color will be appear in the different color. So such colors are known as the complementary colors. So usually whatever the object color is nothing but the complementary color. Now the concept is, now let's come to the point of the absorbed energy. Then where this absorbed energy is moving. Imagine, let us take the temperature of the object initially at the 25 degrees centigrade. Whenever light falls on the object, the particles present in the object try to absorb the energy of the light. So whenever they absorb the energy of the light, their average kinetic energy increases, vibrations increases, and their energy altogether increases. So that increases the temperature. When temperature increases, it tries to release the energy in the form of heat. That is what we call as the thermal radiation. Now, what happens if the color is not get reflected? If everything get absorbed by the body. So if everything get absorbed by the object and no color get reflected, then we don't see any color of the object. So obviously such particular objects appear in the black color. So now let's come to the black body radiation and the black body definition. So in case of the black body radiation, no color should get reflected. All colors must and should get absorbed, and it has to emit all the type of the electromagnetic radiations completely, whatever it got absorbed earlier. Then absorption of the entire electromagnetic radiation by normal bodies is not possible. So normal bodies are completely defective. They cannot absorb the entire radiation whatever falls on their body. At the same time, they absorb only part and remaining get reflected, some get transmitted. Why these normal bodies are not able to absorb the entire electromagnetic radiation or the light that falls on its surface? So in these objects, whenever the light falls on the object, whatever the starting particles present at the striking area, they try to acquire the energy. Once they take the energy, they cannot withstand the entire amount of energy. They have to transform this energy to the next particle. So whenever they try to transform the energy to the next particle, so now here energy has to be transformed in the form of the heat. That takes the time. Since it is taking the time, this particle cannot take the more amount of energy from the light, so that it automatically reflecting the energy back. So that is the reason normal bodies are not the complete absorbers of the all type of electromagnetic radiations. This is where the scientists thought that how to create the black body. So to create the black body, there must be some gap to enter into the body, so that the entire energy electromagnetic radiation has to enter into the body. So that they created a hollow sphere which has a small hole on its wall. Only one inlet and the same exit is present. There is no other areas from where the electromagnetic radiation has to enter, and leaving that option is not there. Only one side it has to enter and the one side only it has to leave. And this is coated inside with a platinum black. So here platinum black, that is nothing but the metal coating they absorb, so that metals again present here. So whenever the light enters into this particular object, it try to get reflected, so that in many directions it get reflected, so that the entire electromagnetic radiation try to move only in the same region and finally get out. So this type of the bodies which allow the entire electromagnetic radiation, so that it undergoes so many reflections and finally leaves the this particular object through the same inlet. Such ideal bodies which absorb and emits all type of electromagnetic radiations are known as the black bodies, and the radiation thus released known as the black body radiation. So apart from this type of the hollow spheres, even carbon black also almost act as the black body. Now let us enter into the another part where we are going to deal with the thermal energy. So now let us take an iron piece, iron rod. So when this iron rod at 25 degrees centigrade or room temperature, when you see this, it looks, we know that, brown color. This brown color is at 25 degrees centigrade when temperature is equals 25 degrees centigrade or below 25 degrees centigrade. Even up to some temperature like 60-70 degrees centigrade also, it looks in the same color. But whenever temperature rises, it gets heated up. When it gets heated up, it looks in the dull red. Again, when temperature increases, it appears in the bright red. Again, when temperature increases, initially it appears white, and later by increasing highest temperature, it almost appears in the blue color. So that here, when you observe the color changes are happening here by increasing the temperature. When temperature increases, the brightness increases. When brightness increases, we can say that the intensity also increases. Now, if you observe these color changes, and by taking this white light VIBGYOR, we know that VIBGYOR colors are arranged like this. These are arranged in the decreasing order of their frequency. Here frequency is highest, here frequency is least, and or else increasing order of their wavelength. Here wavelength is very less, here wavelength is very high. So we know that when frequency is high here, it is a higher energy radiation, and frequency is less means that is a lesser energy radiation. So now here, which is the color initially observed before after heating? Initially it looks red. Which type of the red? Starting part of the red. That's why it looks in the dull red. By increasing the temperature, that means you are increasing the energy. So it comes to the middle part of the red. That's why it looks in the bright red. Again, by increasing the temperature, see all these combinations are giving the white. So that again by increasing temperature, finally it comes to the higher energy frequency, that is blue. So that here it is clearly showing that by increasing the temperature, brightness of the radiation increases, and the frequency of the radiation also increases, so that the color changes. So here we can draw a graph that relates the intensity. Intensity means energy distribution density per area. So when intensity increases, frequency also increases, so that wavelength gradually decreases. So let us make a graph based on this now. So y-axis, x-axis. On x-axis, let us take the wavelength lambda. Say some values are present, 1000, this is 2000, this is 3000, etc. So I am taking the wavelength lambda on the x-axis and intensity on the y-axis. So when you draw the graph, what is happening here? When the intensity increases, wavelength gradually decreases. So that means initially at highest wavelength, the radiation is present. So that the radiation is present like this at highest wavelength. When temperature increases, intensity also increases. So that the wavelength gradually increases and reaches the maximum value, and afterwards again falls down like this. This is the trend of the graph that they observed at a particular temperature T1. When temperature increases, at highest temperature if you take, obviously the graph the intensity will be very high. So that again, initially intensity wavelength increases and then falls down. This is the temperature at T2. So here the combination is T2 is greater than the T1. So this graph explains the relation between the intensity and the wavelength. Then let us try to relate the intensity with respect to the frequency. So y-axis, again we take intensity or else energy distribution density and frequency here. Frequency on x-axis. So what is the relation between the intensity and the frequency? See that when temperature increases, intensity, brightness increases, so that the frequency also gradually increases. So the graph goes that side now. So here it starts like this and showing like this. This is at temperature T1. Again, when temperature is increased, so that the graph is showing like this. This is at temperature T2. Again, if you increase the temperature, the graph again gives the curve like this. This is temperature T3. The relation among these temperatures is T3 greater than T2 greater than T1. And if you observe these two graphs and compare these two graphs, we know that the frequency is inversely proportional to the lambda. That is the reason why here, this is the lambda maximum. And higher temperature, this is the lambda max. So lambda max actually shifts towards the left side when the graph is drawn between the lambda versus intensity. But in case of the frequency, you see this is the nu max at a particular temperature T1, and this is the nu max at a temperature T2, and this is the nu max at temperature T3. So in this graph, the peak shifts towards the right side. So that we can understand that there is a relation between our inversely proportional relation between the frequency and the wavelength. So that particular graph, that is intensity versus the frequency, this was given by Wien's distribution law, in which he says that the nu max is directly proportional to the temperature. This is known as the Wien's distribution law, according to which the nu max always directly proportional to temperature. When temperature increases, nu max value also gradually increases. Now the question here is, why this trend is being observed? See that initially we cannot start a wavelength at lowest wavelength. Lowest wavelength means starting only highest energy. Highest energy we cannot give at a time. Gradual increase of energy been happened here also. So that's the reason why gradually you can give the energy, so that frequency gradually increase, wavelength gradually decrease, so that this graph has to be studied in the reverse manner, not this direction. So if you study this direction, it shows that when intensity increases, wavelength also increases. It should not be studied in this pattern. We have to study in the opposite pattern, so that highest wavelength means lowest energy, starting energy is least. So starting intensity also very less. When the temperature increases, intensity increases, so that frequency increases and wavelength gradually decreases and reaches the maximum value. This is the trend observed. So why this trend is being observed? Because when again we come to the starting part of the electromagnetic radiation, the classical physics says that all type of electromagnetic radiations or energy exchanges happens continuously. That means if any particular body is absorbing energy, it will absorb entire energy of the entire electromagnetic radiation at a time, and also emits all the energy of the electromagnetic radiation at a time. So that is where here the graphs are coming. That is the drawback. This was explained actually by Rayleigh-Jeans. So Rayleigh-Jeans law, according to this law, they explained that energy distribution density at a particular temperature against the frequency is equals to 8 pi nu square by c cube into k into t. Anyhow, we are not interested in these derivations. These are quantum mechanics where we can actually study. So, but I am taking the part of this derivation to make you understand why the graphs are coming like this. So here this particular area KT says that the average energy and here if you see this energy distribution density, that is what intensity we are calling, is directly proportional to the square of the frequency. So that when the intensity increases, frequency also should increase. That means the graph has to come in this pattern. This is what we expected. This is what Rayleigh-Jeans has derived the graph. But in practical, the graphs are coming like this. So they are deviating. This deviation is known as, I'll write down here. Their place is not sufficient. This deviation is known as ultraviolet catastrophe. Why it is called as ultraviolet catastrophe? If you observe this particular trend, whatever the Rayleigh-Jeans proposed, according to this, intensity is directly proportional to the square of the nu. So when intensity increases, frequency also should increase. And it is not happening. It happens only up to certain area. At lower frequencies, it is obeying the law. But when you go to the higher frequencies, it is completely slowly started deviating from the law, and it is showing the another graph. So at higher frequencies means you can see that in the electromagnetic radiation, this is the visible region, and before visible region there is a ultraviolet region, means we are going to the even higher frequencies. So ultraviolet region falls into the higher frequency region. Since this type of the trend is observed in the higher frequency region, so this is named as the ultraviolet catastrophe. Then how to make to understand this deviation and why the graphs, the lights are behaving like this. So this is the what I said, that earlier electromagnetic radiation, according to the classical physics, they thought that the entire electromagnetic radiation energy transforms continuously, not the discontinuously. This is where Planck has come out and he came forward and explained, as he knew the graph before itself, he did not do any new thing here. Only thing he did was to explain the graph, he manipulated this equation, Rayleigh-Jeans equation. So what he said was, this average energy, whatever average energy is there, this average energy cannot be done continuously. It cannot be calculated using the continuous emission and continuous absorption. Why? Because if you want to get, means only he did the mathematical manipulation. That means simply to get the graph, how to get the graph means this equation has to be manipulated. So he said that, Planck's. So this person said that the average energy, whichever is here, average energy is nothing but equals to kT. So this average energy tends to be equals to the kT at low frequency. But when average energy you take, it tends to be zero when nu is infinity. Nu is equals to infinity. So this is at a high frequency. That is also again calculations we are not interested. So that this nu, that means average energy has to be zero at a higher frequency. Then how to make the average energy equals to zero at a higher frequency? So let us see the type of the graphs. And here he proposed one important thing to explain the graph, that is, so imagine this is the graph where I am taking, that is intensity versus the frequency. if continuously energy is released and absorbed according to the classical physics, so here lowest energy is there, here highest energy is there. Obviously average energy lies in this area, that is equals to kT. And he said that if it is not continuously released but discontinuously released, then what could be? See that for that he made that the energy is not coming in the continuous manner but in the discontinuous manner. So here spacing between the lines is very less. Remember, the spacing represents the quantity of energy that released by the body or absorbed by the body. So space is less means it is releasing a small amount of energy continuously. When space is less, more means so that the energy will be released more but takes time. So that here spacing is very less, it begins from the zero. What is the rectangle? Everyone here it says that epsilon, delta epsilon. Or else you can take it as a h nu also. So delta epsilon, if you take the 2 delta means 2 delta epsilon, 3 means 3 delta epsilon, 4th means 4 delta epsilon, and like that. Or else you can take the h nu, 2 h nu, 3 h nu, 4 h nu, like that. So whenever the graph is come like this, when spacing between the rectangles is very less, it almost looks that the graph is going continuously. So again here the average lies in this area, so that it is equals to kT. So here there is nothing that average energy is equals to kT. It appears almost when continuous energy is released in the continuous manner. Now let us take a graph in which the spacing increased. See the graph, now the spacing has been increased. Frequency. So whenever the spacing increases, remember that the average energy gradually decreases because this area completely left. If you include this one also, then the area under this rectangles gradually, if you add and this area also, but here nothing is there. That's why whenever this is added to the spacing, the average energy falls down. If more students got less marks in a class and less students got the more marks in the class, then obviously average energy comes down. The same thing happened here also. And whenever again spacing still increases, that means at highest frequency the energy almost approaches the zero, kT, average energy approaches the zero. So what Planck said was, if to get this type of the curves, only to get the curves he proposed the law. So only to get this type of the curves, we should not consider the energy transmissions in the continuous manner. We have to consider the release or absorption of energy only in the discrete manner. That means then he proposed the law that according to the Planck's, there is no doubt that the electromagnetic waves, radiation. So electromagnetic radiation moves in the form of the waves, but these waves are nothing but they are composed of the small packets of energy. So every wave is nothing but composed of the small packets of energy. Means only these small packets of energy are moving in the form of the wave. So wave is not continuous now. When every packet is different, then obviously wave is now discontinuous, but these packets only moving in the form of the wave. So wave is not continuous, wave is a discontinuous now. So whenever this particular wave falls on any particular object, Imagine here object is there. If it falls on the object, each packet one by one packet get absorbed initially, and whenever it release also it release one by one. So absorption of energy and emission of energy takes place only in the discrete packets of energy. And what could be the quantity of energy that lies with each packet? So he said that the energy of each packet is fixed. That fixed name is nothing but use the quanta. So quantization means fixing. So here these are allowed spacing lines. That means fixed values. What are the fixed values? For example, when you are going a staircase, when you are going to the one floor to the another floor using the stairs, you can step onto the first step next to the second step. So first step is the allowed energy state. Second step is also allowed energy state. But you cannot stand between these two steps on the air. So first step, second step, third step. So they release in the discrete packets of energy, only that much quantity of energy is created. So that packet gets out. Again, when sufficient amount of energy is ready, and that packet comes out, and when absorption also takes place in the same fashion. So that fixed amount of energy associated with each packet is called as the quanta. In case of light, this quanta is known as the photon. Now the question is how this is related to the frequency. We know that frequency is nothing but the number of waves that can pass through a fixed point in a given time or a second of time. More waves if passed through the fixed point in a second of the time, then obviously more packets are passing. Then obviously energy of the radiation also increase. So from here he proposed that energy of the electromagnetic radiation or the light is directly proportional to its frequency. And this proportional symbol being replaced later by using the constant, which is a minimal value, that is a Planck's constant, whose value is equals to 6.626 into 10 power minus 34 joule seconds. It's a minimal value, negligible value. So that value has been taken. So that E equals to h nu. If this is h nu means every packet of energy, every quanta energy is h nu. If you take 2 packets, it is equals to h nu. 3 packets, 3 h nu. Like that, if you take n packets of energy, E equals to n h nu. So n is nothing but any integer value, starts from the 0, 1, 2, 3, 4, all these values. Now, what are the characteristics of the photon? Photon travels with the velocity of the light. Whatever the light speed is there, that is nothing but the photon, because photons only moving in the form of the waves. That's why photons speed is nothing but the speed of the light, and the rest of the mass of the photon is always equals to 0, because it is just only energy packet. It does not carry any mass. And what happens when the photon changes the medium? We know that nu equals to c upon lambda. When the photon changes the medium, see, c changes. That means velocity of the light changes, wavelength changes. So this will cancel each other, so that the frequency remains same. So that means energy of the photons remains same, only its speed changes. That is the photon. Now the question is, how the Planck explained the black body radiation? So initially, whenever we are discussing the black body, we simply said that energy entered into the black body and got reflected many times and finally released energy again back, all the form of energy. So what Planck said was, it is not the surface that is completely reflecting. Actually here the atoms that present on the wall of the black body, which absorbs a part of the electromagnetic radiation and remaining get reflected, but the resultant energy, whatever is coming, is the combination of both thermal energy and the light energy. Initially, we have studied one particular hot iron rod. Whenever you heat it, after a certain temperature, when the vibration of the particles or oscillation of the particles increases, when they get higher energy particles, they start releasing energy in the form of the radiation. That radiation we can see in the form of the light. Here also, since only one outlet is present, this outlet is bringing both light energy and thermal energy out. So that whatever energy was absorbed, entire energy is coming out. So that is what we are calling as the black body, which is absorbing and emitting all the form of electromagnetic radiation. Here, initially whatever these particles are there, they are absorbing energy, a part of amount of energy of the light. So they start vibrating. That is what oscillations or oscillators. These atoms are called as oscillators, which oscillate. And afterwards, they start releasing the energy in the form of the heat, and that heat energy mixing with the light completely comes out so that it looks intensity. That means it is coming, means whatever the energy is coming out of this hole, it is a combination of, it is representing the entire energy form, so that energy density remains same. Density will not change. As long as density do not change, so that intensity also do not change. So he said that wherever thermal energy is involved there, so thermal energy is coming and light also coming, not in the continuous manner, they are coming in the discontinuous manner. Since discontinuous manner is absorbed, so this type of the graphs are coming. And afterwards, how to use this Planck's quantum theory in solving the questions, and what are the values we can use it. We know that E equals to NH nu and E equals to NhC by lambda. N is an integer value, H is Planck's constant, C is velocity of the light, lambda is constant. Lambda is the wavelength of the light, which is not constant. So here two constants are, that is H and C. So these two values always irritate us, because substituting this Planck's constant value and velocity of the light 3.0 into 10 power 8 meters per second. So calculation makes us taking more time to solve the question. So that HC value approximately we can take as 1240 electron volt Nm or 12400 electron volt angstrom. That means when the wavelength of the light is given in the nanometers, we can take this value directly. So HC value 1240 electron volt Nm divided by nanometers. Nanometers cancel out. So you get the answer in the electron volts. And if lambda value is given in the angstroms, then you take this one 12400 electron volt angstroms, and here lambda value is also in the angstroms. Angstrom units cancel out, so again answer comes in the electron volt. But usually in the examination the questions are asked in the joules, not in the electron volts. So that we know that 1 electron volt is equals to 1.6022 into 10 power minus 19 joules. So by multiplying the electron volts, what are the answer we are getting here, and finally we can convert that value into the joules. So this is all about the Planck's quantum theory. I hope you understand. Thank you for watching this class.